All right, hello, and welcome to this recorded recitation. So it is February 29th right now. Happy Leap Day, one of my favorite days of the, I guess not of the year, but of the every 4 years, whatever that's called. That's besides the point. Hope you're having a good spring break. This recitation is, it was supposed to happen the Thursday and Friday before spring break. We canceled it because, nah. So yeah, this is in place with it. Make sure you're getting rest, but still watch this because it's important. We're talking about only induction, not PIE and PHP. So I don't know why that's on the side. Only talking about induction. Let's get into it. All right, so the first slide is about ordinary or weak induction. And I suppose the presence of an adjective and a parenthetical suggests that there are multiple forms of induction. And I'm sure you're very much aware that there are. We'll get to that shortly. But here we have a massive chunk of text. And yes, you can read this. I'm not going to read it out loud because it's very, very annoying to read this out loud. However, I'm still going to take you through it in my own way. So induction is one of the most powerful proof techniques we'll cover in this class. And the reason why it's so powerful is we use it to prove universal claims. So prove something for all integers n greater than or equal to 0, or prove something for all natural numbers. Thus far, when we've seen these universal quantifiers, sometimes we try direct proofs, but that could be really challenging since it's universal. Sometimes we try to make a contradiction, but there are some problems where contradiction doesn't make any sense. So this is another tool in our toolkit that we can use to prove universal things. And the way it works is 2 steps. There's the base case and the induction step. So I changed my mind. I'm actually going to take you through this slide. So induction is showing that some statement, P of n, some sort of proposition, holds for all integers greater than or equal to some n naught. It could be greater than or equal to 1 or 10 or whatever value there. The first step is the base case. We want to show that whatever proposition is true for the smallest value, for n naught. Is there a laser pointer? Yes. So we're showing this proposition holds for everything greater than or equal to n naught. So step 1 base case is saying, I'm going to take the small value, n naught, whatever my lowest value that n could be, I'm going to make sure that the proposition holds for n naught. Why is that so important? Well, if it doesn't hold for n naught, then you're done with the entire proof because you've shown that the statement is false. It doesn't work for all n greater than or equal to n naught. I am so excited about this. Oh my god. This laser pointer is crazy. Okay, suppose the base case checks out and we've shown it to be true for n naught. Great. But now we have to show that it's true for the next value, n naught plus 1, then n naught plus 2, and so on and so forth. And there's a lot of different integers we have to consider. But this is where the magic comes into play. In the induction step, we first do something called the IH, or the induction hypothesis. And what's happening here is we are assuming the proposition to be true. P of k is going to be assumed to be true for an arbitrary value greater than or equal to our base case. This seems pretty crazy, right? We're trying to show P of n is true, and all of a sudden, we're just going to assume that it's true for an arbitrary value of k. That doesn't make any sense. We're assuming what we're trying to prove. But alas, that is the magic of induction. After we make such an assumption, the remainder of our induction step is showing that the proposition holds true for the next value, P of k plus 1. So in other words, with this assumption P of k, we're showing P of k plus 1 holds true. And if we're able to do that, then we're done. Because since k was arbitrary, if k is true and k makes k plus 1 be true, then we have it true for all integers, right? if k equals 3, and p of 3 is true, makes p of 4 be true, then we can let k be 4, and then 4 makes 5 be true, and so on and so forth. It is this domino effect, where if the first domino topples over, the first domino being the base case, and our induction step shows that for any arbitrary domino, if it falls over, i.e. it is true, if that makes the next one fall over, i.e. the next value is true, then everything will fall down. Everything would be true. So that's a long-winded ramble about induction, but it's nice to know a little bit about the structure of it and why these proofs work as such. So that's induction. I hope you can see this laser pointer. Maybe I have to check. And as was hypothesized, there is another form of induction called strong induction. And the difference is basically we need to be stronger. So sometimes in our induction hypothesis, in ordinary induction, we just assume that p of k holds true. But sometimes that's not enough. Or maybe it's just too hard to work with that one piece of information. Strong induction says, okay, base case is going to be exactly the same. Maybe I need to introduce more base cases. And we'll see an example of when we do that, and I'll explain why. But then the induction step is a little bit weird. Our hypothesis changes. Now we're not just assuming p of k. In ordinary induction, it was just p of k. Now we're assuming p of I for everything in this range. Meaning we're assuming p of n naught is true. We're assuming p of n naught plus 1 is true. We're assuming p of n naught plus 2 is true. All the way up to and including p of k is true. This is a much stronger hypothesis because we have much more things to work with in our induction step. We have many more things that we've assumed to be true that we can use in our induction step. So mathematically, we're saying, like, if it was just ordinary induction, we would just hide this, which I suppose doesn't really work with a projector. So just pretend like this part isn't here. And it would just be this. P of k implies p of k plus 1. This is ordinary induction right here, like from here onwards. Strong induction is saying, okay, in addition to this, I'm hypothesizing all of these things to be true. And together, I will show that that implies p of k plus 1. It turns out that ordinary and strong induction are mathematically equivalent. They can both be used for every single induction problem. However, sometimes strong induction is just so much easier. And we'll see example of strong induction questions in just a moment. Cool. One more slide. So here are some tips. Before I go through these, I'll mention that if we haven't already, it will be done very soon. But on Piazza, there's going to be a post that has what we call induction standard deductions, meaning it outlines mistakes that are commonly made during induction, and some of them are seemingly small. However, they do actually alter the meaning of the proof entirely. So first, definitely check out that Piazza question, because that'll help to make sure that the homework proofs that you write up are receiving full points. You really don't want to be losing a point or two just because your wording is slightly off. I know it's kind of irritating when that happens. However, it does change the meaning of the proof. So check that out to make sure you're getting your points. But yeah, let's talk about this. So P of n isn't always going to be given to us in an induction problem. It's not going to say P of n is this, prove blah. Sometimes, if we choose to use this notation, you don't have to use that notation in induction. In fact, I probably won't even write P of n when I go through the problems. But if you like doing this because it simplifies writing a little bit, that's fine. Just before your proof, make sure you define what P of n is. You should say, let P of n represent blah, and then you can use P of n throughout your proof. Otherwise, the proofreader is just guessing at what you mean. We'll talk about this in the problems. But in your induction step, when you're forming a hypothesis, if the question is using the variable n, you want to make a change of variables to a different letter. Usually we use k, so definitely change your variables. And you also need to bound k, and I'll touch on that too as well. It's also good to specify the domain of your variable. Sometimes it's unclear what it is, so it's definitely good practice to do that. This is just a good general tip. You should start by using weak induction, but when you get to your induction step, if you realize that you kind of have to use strong induction, then you can change your hypothesis. But it's not necessarily good practice to start with a strong induction hypothesis and just always do that, because if your induction step only requires a weak induction hypothesis, then that should be your hypothesis. So you shouldn't assume strong and only use like a weak utilization of the hypothesis. It's a bit confusing, but just make sure your hypothesis matches your step. Yeah, and then when you apply your IH, make sure you explicitly mention that you're applying the IH, because usually it's a non-trivial transition in your mathematical logic. So for a proofreader, it's very confusing when a sudden change is made in your math without any citation. So when you apply your IH and you cite it, that helps the proofreader know what's going on. I'll try to touch on all of these as we go through some problems, but I can't remember everything, so we'll see. But yeah, let's do some problems now. All right, so here's our first question of the night. Suppose we have the following sequence. A1 is 1, A2 is 3, and then this is a recursively defined sequence. So the ith term is equal to 2 times A of A sub I minus 2. So 2 times the term twice before it, plus the term right before it. So I made a small mistake. This should be A sub I minus 1. I wrote a 2 here by accident. It doesn't affect anything we've done. It's just it was a tiny mistake there, but thus far everything should be fine. Just take note of that. Back to the video. So, and we're trying to show that A sub n is odd for all integers n greater than or equal to 1. Before we even get into this proof, let's just make sure we understand the sequence. So A sub 1 being 1 means that the first term of our sequence is 1. A sub 2 equals 3 means the second term of our sequence is 3. Now we need to find the third term, A sub 3. So we'll use the equation where I equals 3. So that says it's 2 times A sub 1, because 3 minus 2 is 1, plus A sub 2. Well, A sub 1 is equal to 1, and A sub 2 equals 3. So this is 5. So the third term is 5. Now let's just do A sub 4. So again, A sub 4 is twice of A sub 2 plus A sub 3. A sub 2 is 3. A sub 3 equals 5. So we have 11. And then the next term is 21, and then 43, and then 85, and so on and so forth. And by the eye test, yeah, these all do look odd. However, that's not rigorous enough. I can't just be like, oh, yeah, these are odd, and then it'll continue and they will all be odd. No, we have to use a proof by induction. So there's 2 steps to induction, the base case and the induction step. Normally we handle them chronologically, so let's do that. And in the base case, we need to ensure that the claim is true for the smallest element. And I was intentionally vague with the statement I just said. What is the smallest element? What am I looking for? Is the smallest element 3? Because I see a 3 bounded here. Is it 1? Because that looks like it's the smallest element of my sequence. What's going on? The way you figure this out is you need to first determine what are you inducting on. Let's write that here. So yeah, what are you inducting on? This is the first question you should ask yourself before you even jump into a proof. And what this is asking is, what is the variable that is changing in the question? Or what is the variable that is guiding our proof? So when we read this question, there are a lot of variables, like there are i's and there are n's. But at the end of the day, we're trying to show a sub n is odd. And n is this variable that is changing, that we need, that when it changes, we also need to show that something is true. So you basically look like, what am I trying to prove is true? In this case, a sub n is odd. So in this case, we're inducting on n. So when we come back to our base case, we ensure the claim is true for the smallest element. We need to be thinking, what is the smallest value n can take on? So in this case, we would test n equals 1, because the question says to prove it for all integers n greater than or equal to 1. Okay. Well, all we need to do is show that a sub 1 is odd, right? To show that the proposition is true when n equals 1, we're trying to show a sub n is odd, so just replace n with 1, and we're just trying to show a sub 1 is odd. Well, we're given by the definition of the sequence that a sub 1 equals 1. So we're given that a sub 1 equals 1, and 1 is odd. So the base case checks out. Base cases are usually very simple. There's not that much to it, but it's an important part of the proof. Let me just move this down a bit so there's some room. So now we have to do our induction step. And for the induction step, first we make our hypothesis. First, we assume the claim to be true for some arbitrary value of k. So I'm just going to go ahead and write out a full-formed induction hypothesis, and then afterwards I'll talk you through it to see what's going on. Okay, so here's our induction hypothesis. Let k be an integer, and k be greater than or equal to 1. Let it be arbitrary. This first sentence is super important, and we'll touch on what's going on here in a moment. But then the second sentence, we will assume that a sub k is odd, right? This is the assumption where I was like, oh, we're assuming what we're trying to prove. This is what's going on. We're just assuming that a sub k is odd. And we're going to eventually use that in the next step. But let's take a moment to parse through this induction hypothesis. And let me label it IH. So there's a couple things going on. First of all, k appears. There's no k in our question, but remember I talked about the change of variables thing. Yeah, that's exactly what's going on here. I could have said let n equal k in the integer set to fully specify that k is taking on the role of n. Normally I do this, but like I suppose it's not super necessary for you to do. I still think that I mean, either one of these is fine. But anyways, k is taking on the role of n, which means to make that clear, we need to specify its domain and its bounds. So n was an integer. So we're saying k is also an integer. And n is greater than or equal to 1. So k is greater than or equal to 1. This value, we always have to do a bound. Like every single time in our induction hypothesis, there has to be a bound. Even if it seems useless. Like even if the domain implies what the bound should be, you always need a bound. And this bound, the value, is always going to match your base case. Whatever base case you have, we use n equals 1. That should be the value that appears right there. So this is what an induction hypothesis looks like. Change of variables, do the bounds, and we must say that this value of k is arbitrary. It is not a specific value. It's not every single value all at once. It is an arbitrary value. because in the next step, when we show p of k plus 1 to be true, we're relying on k to be arbitrary because we're trying to show for all values. So these words, also very important. That's a lot of time spent on the induction hypothesis, but it's very important. It's very easy to lose points by not having a well-formed induction hypothesis, so this is critical. Now we finish up the proof. So now that we've done all of this, the whole point of the induction step is to show that the k plus 1 case is true. Remember in the slides we said p of k implies p of k plus 1. There's no there's no p notation here because I didn't feel like defining that, but we're trying to show that the k plus 1 case is true. The proposition of something being odd holds for the value k plus 1. So in this case, we're trying to show a sub k plus 1 is odd. Okay, well, what is a sub k plus 1? I mean, it's not just like with n equals 1, we were just like, oh, it's 1. We're told that, but I don't know what k plus 1 is. So I don't have like a specific value to work with. But I do have like this equation here, which seems useful. So maybe let's use this, but wherever we see an I, we'll put k plus 1. So a sub k plus 1 is equal to 2 times a sub k plus 1 minus 2 is k minus 1, plus k plus 1 minus 1. Did I mess this up? This should be minus 1. Okay, and then plus a sub k. Here's where people usually fall into the trap. This is currently wrong, what we've done. We actually can't really start out with this. Why? Why not? I mean, it's right there. Why can't we use it? Well, I was a little bit tricky, right? This equation up here only holds when I is greater than or equal to 3. And we just falsely assume that, oh, k plus 1 is probably greater than or equal to 3. But it isn't. It's not always greater than or equal to 3. Because we said in the induction hypothesis, k is greater than or equal to 1. Which means if k we chose happened to be 1, an arbitrary value that happened to be 1, then here, k plus 1 would equal 2. Which means we can't use that equation. So whatever work we do, it's not going to apply when k plus 1 equals 2. That's not good. So what do we do? Well, if we just change this value to be k greater than or equal to 2, then we're chilling because k plus 1 will be at least 3. And then we can use this equation because, this left term is, the subscript is at least 3, and here it would be. So we want to make this a 2. But we can't quite do that because it doesn't match the base case. Remember I said it should always match the base case. And the reason for that is not that hard, but it's a little complex to put into words. Let's suppose we proceeded as normal. We let k be greater than or equal to 2 and just ignore that it doesn't match the base case value. Well then here we would show that p of k plus 1 is true. So we would, if k is equal to 2, we would hopefully show that p of 3 is true. And then p of 3 would imply p of 4. That would be true, and then p of 5 would be true. And in the base case, we've only shown that p of 1 is true. But we never showed that p of 2 is true. We've only assumed it to be true. So here, we're doing the assumption. It's here, whatever we do down here, that we're proving. So we need to make sure whatever we do in the base case and the bulk of the induction step covers everything. So, okay, let's still keep this as 2, but we can avoid a mismatch by just adding another base case. We did n equals 1. Why not do n equals 2? Because then the base case will match the bound. So let's do that. And it's very similar to n equals 1, right? When n equals 2, we want to show a sub 2 is odd. We're given that a sub 2 equals 3, and we know that 3 is odd. If you want it to be really good, you could say 3 equals 2 times 1 plus 1, but I ran out of space and I didn't feel like writing that. But now we're chilling. We have 2 base cases, and we've changed our induction hypothesis. Good. So everything seems good. We can proceed with this. So now we don't have to worry about this equation being wrong, because this subscript will always be at least 3. And so we can use that formula. Okay. Remember, we're trying to show that this guy is odd. And we've expressed it in terms of 2 other guys. What do we do? I don't know what that is. And I don't really know what that is. Or maybe I do. A sub k, where have I seen you? Well, I saw you down here. We assumed that a sub k is odd. Well, that's helpful. If a sub k is odd, then I can represent it as 2l plus 1 for some integer there. So a brief disclaimer, I forgot to cite the IH in this question. It is completely my fault. Make sure you do it. But as you get on to question 2 in this video, you'll see that I talk a lot about it. So now you might be tempted to be like, okay, I see a 2 here and I see a 2 here, so let me factor them out and say this is equal to this plus 1. And if I can say that this is an integer, then I'm done, because I've represented something in the form of an odd integer. Can I just say that's an integer? Normally we sort of be like, oh yeah, I mean, of course it is, right? L is an integer, and a sub k minus 1 is surely an integer. But is it? What is a sub k minus 1? We don't know anything about it. The only thing that we know to be certain in our induction step is that this equation holds, and because this is something that's given to us, the only other thing that's given to us besides these nonsense things up here, base cases, is that a sub k is an odd integer. Those are the only things we have to work with. Things that were absolutely for sure given to us, and things that we have assumed in the induction hypothesis. We have only assumed a sub k is an odd integer. So I don't know if a sub k minus 1 is an odd integer. I don't know if it's an integer at all. So what do we do? I'd love to substitute it with something like this, 2l plus 1, because that helped out tremendously, but I can't unless I strengthen my induction hypothesis. If here I assumed both a sub k and a sub k minus 1 were odd, then I could do a little bit of substitution here and we'd be living a happy life. And luckily, we can do that. That's the entire purpose of strong induction. When what we assume seems like it's not taking us as far as we want, we add more to the induction hypothesis. We assume more things. So I'm going to rewrite this induction hypothesis, and we'll see what a strong induction hypothesis looks like. So all that has changed is the second sentence. We still change the variables to k. It's an integer greater than or equal to 2, because that's our base case. But now we're assuming that everything from 1 to this arbitrary value of k, so a sub 1, a sub 2, a sub 3, all the way up to a sub k, we're assuming all of those are odd. So that's what this value j is doing. It's sweeping between 1 and k and saying everything in this range I am assuming to be true. So, okay, let's take a moment to parse through this again. First sentence, like I said, the same. Here, we're assuming something for all j within a range, and these bounds are important. So the upper bound should be this arbitrary value, because that's the point that we want to stop assuming things for, right? In ordinary induction, we just said, oh, p of k, we're assuming that to be true. So we need to stop when we reach p of k. But we need to start actually at 1. So the lower bound is the smallest base case. So why is that the case? Because here, if we're showing a sub k plus 1 to be true, and maybe k plus 1 equals 3, so we're trying to show a sub 3 is true, well, we would want to know that a sub 1 is true and a sub 2 is true, not just a sub 2. We're assuming everything from the smallest possible value that could be considered up to k. So there are a lot of different bounds going on, but it usually follows a pretty simple pattern. This is bounded by your largest base case. This is your smallest base case. That is the variable that you change to. So I know I'm doing a lot of talking in this problem, but I did promise during the slides that I would take you through this very carefully and make sure you're not losing points. So there's a lot of moving parts to the hypothesis. It is critical to make sure it is correct. I know some of you are like scrubbing through this video like, man, this guy's so boring. Why am I wasting my life listening to this? To the people that are actually listening to this, good. Don't lose points. You know, maybe write it in your homework solutions. I watched that recitation and Ishaan said to write this or whatever. I don't know. Just have fun with it. All right, let's finish strong. So let me just erase this. So this is fine. We can still substitute 2l plus 1 for a sub k, because we've assumed that in the hypothesis. But now we're also assuming a sub k minus 1 is an odd integer. So I'll do the same thing. This is 2 times 2m plus 1 plus this 2l plus 1 for some integer m. And again, we're trying to show that a sub k plus 1 is odd. So we just have to write it in the odd number form. So it turns out that we can say plus L plus 1, that these two are equivalent. And now we know for certain that since m and L are integers, then 2m plus L plus 1 is an integer. And that completes the proof by induction. This example was the most important thing I could have possibly done, because we went through everything. And this is exactly how induction proofs could go. You start out small. You start out with your base case. You make your weak induction hypothesis. Then in your induction step, you make sure that whatever equation that you're working with is actually something you can use. We realized, like, hey, this doesn't really work when k plus 1 equals 2. So we went back and fixed it. We changed our bound. We added another base case. That fixed the problem. But then we were like, hey, I can't make that much progress. I need more strength. So we changed the induction hypothesis. And we landed on strong induction. So this covered everything there could be done in induction. I hope that was helpful. Luckily, there's 2 more questions to do, but I promise they won't be as painful as this. I'll try to make them a little bit easier to get through. Okay, here's our next question. Prove for an arbitrary positive integer a that for all positive integers n, that a to the n minus 1 is divisible by a minus 1. So we see a universal quantifier, so we're prompted to think induction. And so let's try that. The first question you should ask yourself, what are we inducting on? What is the value that's changing? That when it changes, we still need to show that it's true. And it seems like there's a couple of things that could be changing. A is an arbitrary positive integer, so are we considering like for all A? But then there's also a for all n. What's going on? Well, you see what you're trying to proving. A to the n minus 1 is divisible by a minus 1. What this is saying when a is an arbitrary integer, it's saying, suppose I have a mystery positive integer. I'm not going to tell you what it is. I'll tell you later, but I'm not going to tell you what it is. You're going to have to provide me a proof that together, if we go through every single value of n, when I give you my mystery number, when we compute this for every single value of n, it'll be divisible by a minus 1. So a is sort of this mystery entity that you don't quite know. I have choice in what that value is. But together, we're going to show that every single positive integer n yields this relationship. All of this to say is that n is the value we're inducting on. So the answer to this is n. So now we jump into solving it. So in the base case, we show that the claim is true for the smallest value of n. So we're going to test n equals something. What is the smallest possible value of n in consideration? Well, if we're showing something for all positive integers n, the smallest value of n is 1. So we'll test n equals 1. So we want to show that a to the power of n, or in this case, a to the power of 1 minus 1 is divisible by this a minus 1. Well, a to the 1 minus 1 equals a minus 1. And, well, that's equal to 1 times a minus 1. So it's obviously divisible by a minus 1. This is a bit going too far because the definition of divisibility is that our definition of divisibility says that x is divisible by y if we can find some integer z such that y times z equals x. So a to the 1 minus 1 is divisible by a minus 1 because there exists an integer such that y times z equals x. A minus 1 is divisible by a minus 1. Like, come on. All right. Cool. Let's move on to the induction step. Again, we're going to start by making the hypothesis, which has a couple of points to it. We do a change of variables. We bound the new variable. And we mention what we're assuming. So our IH is there. Let k be a positive integer and greater than or equal to 1 be arbitrary. That's sentence 1. This is the domain because that's the domain for n. It's greater than or equal to 1 because the smallest value n can take on is 1. That's sentence 1, and it's arbitrary. Then we say what we're assuming. We assume that a to the power of k minus 1 is divisible by a minus 1. And this entire thing is the induction hypothesis. So this conglomerate is the IH. Cool. Now we get on to the fun part. So now the next part is to show the k plus 1 case. WTS, we want to show that the k plus 1 case is true. So we want to show that a to the k plus 1 minus 1 is divisible by a minus 1. Right? When n is k plus 1, we want this to be true. Okay, so this is what we're dealing with. In the previous question, we had something to work with. The question gave us a formula for a sub k plus 1, and we just chucked in the formula and we were chilling. What do we have here? I don't know. Like, what am I supposed to do? So this is where the seeds of induction are getting planted. That doesn't mean anything. I thought that would sound profound, but it's not. More often than not, you're not given something to work with. So you just have to work with this. You have to use some sort of algebra skills to bend it and twist it in a way that you want. But how do I know what to do with it? In induction, we always use the induction hypothesis. We're making an assumption right here of something to be true. We better use that. Otherwise, what's the point? Right? We've done something so powerful. We've assumed a to the k minus 1 is divisible by a minus 1. We better, gosh darn, use that. So somehow we have to bend this in a way that we get a to the k minus 1 somewhere, so we can perform some sort of substitution. So I can make this look like it's a to the k pretty easily, right? If I just say a to the k plus 1 is equal to a times a to the k minus 1, that looks a little bit better, right? We're almost getting something that looks like this. In fact, it's right here, but these are, two different terms. So I can't quite do anything because it's a times a to the k minus 1. But if this was like minus a times 1, then I could factor out an a, and then we'd be kind of chilling. So what if we do that, right? What if we literally say we had an a times 1 term, right? Like if we factored out the a, we'd be fine, but we can't do that because those two aren't equivalent. So I've subtracted out a. Why don't I just add back in a and tag along the minus 1 term? Right? These two are now equivalent. All I've done is just the same two terms have been pushed apart, and I've subtracted a and added a. So I've just added 0. Now I can factor out an a from these two terms and throw in some parentheses. Now we're starting to get somewhere, right? That looks a lot better. We can now work with a to the k minus 1. So this is what I'm saying. We didn't have anything to work with, but we knew where we needed to get. We wanted to see this term somehow, somewhere, so we could do a substitution. And the only way to do that was just to use some sort of algebra skills, adding a form of 0. I can't teach you algebra. That's not my job. But I can try to teach you to be creative. I didn't see the a to the k minus 1 here, so I just pushed it so that way I do see it, right? I wanted a minus a times 1, so I was like, okay, let's just say I have a minus a plus 1, and then adjust later. And we got to here. So, okay, we've seen this a to the k minus 1. We want to use our induction hypothesis, because we said it's divisible by a minus 1. I removed the definition of divisibility, but I kind of needed it. So if a to the k minus 1 is divisible by a minus 1, then a to the k minus 1 is equal to q times a minus 1 for some integer q. That just follows from the definition of divisibility. It's what I wrote up and then promptly erased. So that's exactly what it means. So why don't we just shove this in for a to the k minus 1. And now I'm going to harp on this fact by IH. I'll be completely honest. I forgot to do this in the first question, but I just cannot re-record the video. It is like 12:30 a.m. and I have so much stuff to do. So it's my mistake for doing that. Okay, so yes, we are citing the IH because this simplification, a to the k minus 1 equals q times a minus 1, it's non-trivial. Like that's not an intuitive simplification. So we tell the reader that we can do that by the IH because that's what we assumed here. Very important you do that so you don't lose points. I would have lost points on question 1 because I didn't completely do that correctly. My bad. Always, always, always cite your IH. Always do it. Cool. Okay. Great. So we've broken it down. We've reached, this is like our checkpoint. This is checkpoint. Checkpoint 1 is being able to use your induction hypothesis, right? Performing that substitution. Checkpoint 2 is finishing off the proof. Showing that whatever we're trying to do is happening, that something is divisible by a minus 1 in this case. So to do that, we just have to write it in this form. Something times a minus 1, because that's the definition of divisibility. So, miraculously, I see an a minus 1 here and an a minus 1 here, so I can factor that out. And from the first term, I get aq, and the second term, I get 1. And well, since a and q are both integers, a is an integer because we're told it's a positive integer, q is an integer because it's the definition of divisibility, then aq plus 1 is an integer. So I've represented it like this, therefore I'm done. A to the k plus 1 minus 1 is equal to that, so this is divisible by a minus 1, because I found such an integer there. That's it. Make sure you cite your IH. That's super important. And there you go. That's the second question. Okay, for this question, I'm going to ask you to just refer to the PDF that we posted online with the questions. I'm not going to write it on the board because it would take too much space. So yeah, make sure you have that available. Make sure you understand the question, but we'll go over it. So there are these two people in this question, Ishaan and Alyssa. I don't know, that Ishaan guy's kind of weird. And there's these two bags that are non-empty, but they have marbles in it, and an equal number of marbles in each bag. I am losing my voice. And then Ishaan and Alyssa are playing this game where in one turn, someone chooses a bag and removes some amount of marbles in it. And then the next person goes, they choose some bag, remove some marbles from it. So on and so forth. Whoever removes the last marble wins. And you can remove however many marbles you want, as long as it's from, all the marbles are from the same bag. So it's kind of sad. This is my last time teaching this question. I enjoy teaching this question in person because I like to simulate the game with someone. So since I don't have anyone here, sad, I will pretend that I can hear what you're saying, and you are going to play the game along with me. And I tend to think of myself as a relatively nice guy, so I will let you go first. So make your move. Okay, so you chose 2 marbles from this left bag. Cool, good choice, good choice. I'm going to remove 1 marble from the left bag. Okay, your turn. Okay, so you're going to choose 4 marbles from the right bag. All right, that's fine. I'll choose 1 marble from the left bag. Now what are you going to do? You can't choose 2 marbles from a bag, because then I would just choose 2 marbles. So maybe you just choose 1 marble. I'm going to pretend you're saying that. So let's say 1 marble from the left bag. Well, I'll choose 1 marble from the right bag. So your turn. 1 marble from, I guess, the right bag. Well, I won. I chose the last marble. Sorry, I'm just good at this game. Should we try again? Okay, let's try it again. I'm simplifying it down. Let's say there's 3 marbles only. Go ahead, pick your marble. 2 marbles from the right bag? Are you sure about that choice? Okay, all right, let's just do it. 2 from here. Well, I'll choose 2 from the left bag. Your turn? 1 from the left. All right, well, I win again. I got the last marble from the right bag. I won twice. Are you sure you're good at this game? I don't think so. I think I'm pretty good. So, what's going on? I let you go first twice, so I went second twice. I won both times. Can I always win? Or did you just play poorly and maybe you could have won? Well, by the way I was playing it, I gave you some opportunities to win. But I claim that I would always win if I let you go first. And why is that? You may have noticed that you ran into a really dangerous position in the first game when there were only 2 marbles left in both bags, right? Because you couldn't choose 2 from one bag because I would just choose 2 from the other. So you chose 1, and then I chose 1. Then there was 1 marble left in each bag, and still you were in a bad position. So, you lost. And in this last game, same thing. There was 1 marble left at the very end, and you lost. There was no way for you to win. And even when there was 2 marbles left, there was no way for you to win. We started off with 3 marbles. So that's interesting, right? If I can take a game and reduce it down to 2 marbles in each bag, then I know for sure I'm going to win. Or even if I reduce it down to 3 marbles in each bag, I can also probably still force a win. So, how can I do that? The way this could work is if I just copy you, right? If there is a bag, let's say 2 bags with 6 marbles. Whatever your first move is, say you choose 2 marbles in the right bag. I'm going to choose 2 marbles in the left bag. So after game 1, or after round 1, it is your turn, but we're dealing with the smaller game where there's only 4 marbles in each bag. So your turn. Maybe you choose 2 again from this bag. Then I'm going to copy you and choose 2 from the other bag. And again, back to your turn. Now we're reduced to the game state with 2 marbles in each bag. And we know this is doomsday for you. You're not winning this, no matter what you do. If you choose 1, I'll choose 1. And then you choose this marble, I win. So it seems that no matter what, if there's an equal amount of marbles in each bag, and you go first, and I copy you, I always win. Are we sure? The only way we can know for sure is to prove it. So I've written in very poor handwriting because I'm tired and my arm is tired, a formalization of what we just came to. That if Ishaan goes second, then in any starting configuration, meaning we have bags with some positive integer marbles in each bag, but an equal amount in each bag, that Ishaan will always win if he copies Alyssa's move, Alyssa went first, in the opposite bag. So if Alyssa chooses 3 marbles from the left bag, then Ishaan will choose 3 marbles from the right bag. That is just what we've deduced so far in that exercise that just happened. So now we just need to prove this to be true. So, seems like induction is going to be the way to go because we need to show it for all values of n, not just 2 marbles or 3 marbles. No matter how many marbles are in each bag, we have to show it to be true. So let's do induction. Our base case should be the smallest value of n. So we'll test n equals 1. Well, if there's one marble in each bag, well then, if there's one marble for each bag, Alyssa has to choose a marble. She can't just pass. So her only choice is to choose one marble from some bag. So Ishaan follows his strategy, copies for the other bag, and removes the final marble. He wins. That's the base case. Now we'll get into the induction step. And remember, we need to make our hypothesis, our assumption. But I claim we can already start to think ahead a little bit. When we prove the k plus 1 case, we want to use our assumption. Right? So the k plus 1 case, like eventually we'll reach here, I'll draw my line and I will say, want to show k plus 1 case. Like we'll consider the case like where there's k plus 1 marbles, and we'll say that, okay, we're going to show that Ishaan still wins, right? This is what we'll eventually get to when we make our hypothesis. But we know that we'll have to use whatever we assumed. If we do ordinary induction, then the only thing we would assume is that if there were k marbles in each bag, then he would win. But we have k plus 1. We don't know how Alyssa's going to behave. The only way k plus 1 in each bag could reduce to k in each bag is if on the first turn, Alyssa chooses a single marble from one of the bags. But we don't know if she's going to do that. She can behave however she wants. So we can't just say, oh, she chooses one marble and then Ishaan follows suit, and then we have the k bags. No good. Can't do that. We don't know what she's going to do. So already we can say that, like, okay, maybe just assuming this one thing is no good. Maybe we need to assume something stronger. And so that's exactly what we'll do. We'll form a strong induction hypothesis. Okay, I know the handwriting is pretty ugly, but I'm really tired. It is the same structure of a hypothesis. It's the same thing we've always done, where it's sort of like a two-sentence thing. It just looks a bit longer. Sentence 1 is the exact same thing. Change the variables to k, specify the domain, it's a positive integer, because the question told us that they're non-empty bags. So there's at least one marble. N is the number of marbles. So it's a positive integer greater than or equal to 1, and it's arbitrary. Sentence 1. Then we state what we're assuming. It's a strong induction hypothesis. So we're assuming for all j from 1 to k, remember, this bound is always the variable that we change to, and this is going to be your greatest base case. In this case, we only have one base case, so we'll keep it at 1. For all j within that range, we're assuming the claim to be true. Or in words, that Ishaan will always win by following the strategy if the starting configuration had j marbles in each bag. That's our assumption. So, this is good. This is good. So we start with k plus 1 in each bag, and we don't know much. All we know is Alyssa is going to remove some amount of marbles from one of the bags, right? Suppose she removes m marbles from the first bag. So then this bag has k plus 1 minus m marbles in it. And if Ishaan's following the strategy, then he would remove m from the second bag, and that would also have k plus 1 minus m. So the same number in both of these bags, we said, if there's the same number in each of the bags, Ishaan will win, as long as that number falls within the range 1 to k. That seems pretty okay. So this is basically what I said out loud. If Alyssa removes m marbles from a bag, on her first turn. We don't know what m is. She just has to remove something. Ishaan will follow the strategy and remove m from the other bag. So then both bags now have k plus 1 minus m marbles. And our induction hypothesis said, hey, if there's the same amount of marbles in each bag, Ishaan's going to win. So we just say, oh, by the IH, Ishaan wins. Not quite done. Not quite done. We're close to being done. This was a little bit dubious, this last transition here. Like, yes, we would want to apply the IH here. But we can only apply the IH if we assumed what is shown to us. K plus 1 minus, like, yes, there are the same amount of marbles in each bag. However, my induction hypothesis said only for 1 up to k. Only when there's those amount of marbles, if there's 1 marble in each bag, or 2 marbles in each bag, up to k marbles in each bag, only then could I assume that Ishaan would win. So in a world where k plus 1 minus m equals like k plus 10, then I couldn't conclude this because I didn't assume it for k plus 10. I only assumed it up to k. So to make this transition correct, we would have to show that k plus 1 minus m always falls in this range 1 to k. That is an important step. Well, what is m? M is the amount of marbles that Alyssa removed. So at least, she must have removed at least 1 marble. She cannot pass and take 0 marbles. She has to have removed 1 marble. The most amount of marbles she could have removed is, well, all of the marbles from 1 bag. She could have just done that. She could have removed k plus 1. Well, if m equals 1, then here we have k marbles in each bag. That's fine, because we assumed it for k marbles in each bag. And if m equals 2, then it would be k minus 1. We're still fine. But if m equals k plus 1, this would say we have 0 marbles in, well, like after the first step, there would be 0 marbles in 1 bag. And then Ishaan removes 0 marbles from the other bag. So we would technically be done there. But here we're saying, oh, by the IH, Ishaan's guaranteed to win. So technically, this still follows for when m equals k plus 1. That's incorrect, because the IH doesn't apply for m equals k plus 1. All of this is to say is that we just need a little bit of casework. So case 1 will be when m is in between 1 and k. Then everything I do here is completely justified, because this value will always be in between 1 through k. Just to verify it to you, so here is the full math to verify it to you that this value will always be in between 1 and k. If, in this case, m is in between 1 and k, we just negate m, add k plus 1 to all sides, and we have it in the range. So the IH applies. So that's why we need that case. And then we do need case 2. So case 2 occurs when m equals k plus 1. So if Alyssa... So yeah, the second case is a little bit shorter. It's just that if m equals k plus 1, so if Alyssa removes k plus 1 marbles from 1 bag, then Ishaan removes k plus 1 from the other bag, and he wins. It's done. So it's basically like these first 2 steps. We couldn't include this value up here, because then we would say these last 2 steps apply for when m equals k plus 1. That's no good. The IH does not apply when m equals k plus 1. So this separation is necessary. I don't know how long this video is because I haven't edited it yet, but there's a lot of stuff. There are a few major takeaways. Number 1, did I cite my IH? Yeah, I did. Good. Okay. Number one, know how to write an induction hypothesis. There's a couple of moving parts, but just know the parts of it. I told you, I gave you the template. You do your change of variables. You give the domain. You bound it. You state what you're assuming. You just need to do that. You state that it's arbitrary. You do that, you'll be fine. Learn how to write an induction hypothesis. 2, in your induction step, if you don't know where to go, you at least know that you have to use your induction hypothesis at some point. So use your creativity to get to a position where you can use your induction hypothesis. 3rd, in your induction step, make sure you actually can use your induction hypothesis. Sometimes the bounds are a little bit off. You have to be careful with your bounds. So whenever you apply your induction hypothesis, make sure for certain that the induction hypothesis applies. In this case, it didn't. There was an edge case that we have to consider. These are all just these small little things that appear in induction problems. They're so hard to recognize. But with some practice, with some detection, some playing around like this, always being on your toes, you can catch some of them. My voice is absolutely shot. I'm going to feel it tomorrow morning. I'm so exhausted. I really hope this was helpful to you. Induction, so important, very powerful proof technique. It's going to take you a long way. I hope you have a good rest of your spring break. If you're watching this during spring break, I appreciate you. I love you. Thank you. And yes, I'm excited to see many of you back in class in a couple of weeks. So thank you. Have a good night. And yeah, talk to you soon. Have a good one.